Feed 2.3 is a case of geometric sequence or exponential decay. You can see from the graph we start at 180, and then we drop down to 614. So you see that exponential decay. That tells me that there's a common ratio figure and it's between 1 and 0. Or if we write the notation less than, we could write it like that. In order to find a rule for the graph, we'll write out what we know. The first term is equal to A is equal to 280. The sixth term, A times R to the power of 5 is equal to 14. And you're strongly recommended to do this on your calculator. On the main screen, I've entered A is equal to 180 using the simultaneous equation solver, and A times R to the power of 5 is equal to 14. Solving for A and R, and when I do that, A is equal to 180 and R is equal to 0.60. So I can straight away write out the equation as Tn times 0.6 the n minus 1. Now from there on in, I can use this in order to make predictions and also check estimations off the graph. Now after 3 months, we're asked to look at the graph and the approximate figure. So reading up from 3 and across to the y-axis, bit of estimation there. I'll say around about 65 milligrams. Now that's very much an estimation. If I was to use the equation, putting that through, 64.8 milligrams. So not bad, I was pretty close to the estimation from the graph. Continuing that through for part D, 180 times 0.6 to the 8 is equal to 3.02 milligrams. Now E, we want to determine when the radioactivity in the sample will be below 1 milligram. So what I've done, I've set up on the explicit range the function A and E is equal to 180 times 0.6 to the n minus 1, and rolling that down, you can see that it takes a while to get down to 1 milligram, but the 11th month has a 1.09 figure, so we would say, recording what we've got for the 11th month, so we would say after 11 months. It might pay to put down what the 12th month figure was as well.